All right. Yesterday we started with some basics of graph theory, and we talked about bipartite matching problem. And we, discussed this complex algorithm called the augmenting path algorithm. My apologies for those of you who had kind of trouble understanding or following some arguments and steps of the algorithm. This is my first time covering and teaching, this algorithm in public. I might have some, issues in terms of delivering the ideas to you. But I try to write down my lecture notes as easy as possible. So do spend some time, going over the details written in the note. But if you have any questions, please let me know. I was thinking about the easiest way possible to, organize materials over this course. But I realized that the augmenting path algorithm is the central part, and it's for the matching topic. Okay, so even today and tomorrow, we're gonna rely on some results from yesterday. So it will be very useful if you understand and follow or remember some of the kind of nice arguments about how to guarantee that the maximum matching is found for a bipartite for a bipartite graph. Okay. I'm gonna review some of the steps today also, but if you please, if you still have some issues about following the ideas, just please read the lecture note for lecture 2. Yeah. But before we get started, is there any question? Did you find any typos? I already got some from a student. If you have spotted any typo, please let me know. Then I will just update that for a future reference. Okay. All right. Yeah. All right. So that was spotted by a student. Thanks. You got into the same issue. Thanks. Any other typo? Thank you for spending your time reading the note. Okay. All right. So we're gonna quickly review the things that we talked about yesterday. And so yesterday we focused on maximizing the number of edges in a matching, right? But today we'll look at something different in the sense that edges have different weights. So not all edges are equal. Some edges are more important than others. So we want to consider that variant. But the algorithm for, this, weighted case, dealing with different weights of the edges, the algorithm is a bit different from what we learned from yesterday. Of course, the algorithm from yesterday can be extended to this weighted case, but I take this opportunity to cover a different algorithm, which is based on something called linear programming. Okay. Linear programming is quite common for industrial engineering people, but maybe it's not as common in computer science or electrical engineering. After this lecture and today, I will perhaps kind of distribute some of the lecture notes from previous course of mine on linear programming. So if you have trouble following, some stuff about linear programming, the topic itself is quite well known, so you can also Google it and use Wikipedia to follow or find some relevant materials. And if I have enough time, I also want to cover something called the perfect matching. So the perfect matching seeks to cover all vertices. So a maximum matching just maximizes the number of edges. It's possible to have some vertices that are not covered by a matching edge, but a perfect matching has to cover all vertices. If such a thing exists, we call it a perfect matching. Okay. So, and there's a condition. So it's not that a perfect matching exists for all graphs, but we can characterize a situation when a perfect matching exists. And the characterization is called Hall's marriage theorem. Okay. And the proof of it will use some of the arguments from yesterday. So that's why I'm asking you to read the lecture notes. Okay. All right, so let's go over some stuff from lecture 2. So the main idea behind the augmenting path algorithm are as follows. So we have a bipartite graph and we have a matching. Okay, and we say that a vertex is M exposed if this vertex is not covered by a matching edge, in a sense that it's not incident to edge zero matching. So in this example, we have these two vertices at the end. They are not covered by a matching edge, so they are called M exposed. And we take a path, and this path is called M alternating if the edges are alternating between matching and non-matching, like this example. So we have edge zero matching, and the next edge has to be a non-matching edge, and the next edge has to be part of matching. So if you keep this process, the resulting path is called M alternating. Okay. What's important for the algorithm is this notion of augmenting path, right? So augmenting path is an alternating path, but with the additional property that the endpoints are exposed, like this. So if you have an augmenting path, what we do is we switch the rows of matching edges and non-matching edges on this path. You don't touch any other edges, or you just change the status of the edges over the path. So if you do this, the augmenting operation, you have, let me draw. You have E1, E2, E3, E4, E5. So E2 and E4 were part of the matching, but if you do this augmenting step, E1, E3, E5 become matching edges, and E2 and E4, they leave the matching. Okay. And again, by the definition of this augmenting path, it has to end with non-matching edges, and it has an alternating structure. So by this definition, it has to be an odd length. There has to be an odd number of edges on this augmenting path. So if you switch the role, then we get one more edge in a matching. Okay. So if you find an augmenting path, you can always increase the matching size by 1. That is the idea. Okay. And in this example, you look at a path from U1 to V4. Now, so U1 and V4 are M exposed. So these are exposed. Again, it means that they are not covered by a matching edge. Then you take this augmenting path. This is alternating, which has both ends exposed. If you do the augmenting step, we get a better matching. Now you see that all vertices are covered, and it's called a perfect matching. We're gonna get to this definition later. Right. So this is the augmenting step. And formally, what this augmenting step does is expressed by this operation called symmetric difference. And the symmetric difference is just, let me write down the definition again, is you take the union of, so basically if you draw the Venn diagram, so you just remove the intersection and you keep the elements that are excluding the intersection. That's the symmetric difference. Okay. If an edge appears in both M and P, you take them out. If an edge appears exactly one of these M and P, you take them. Okay. That is the symmetric difference. That's what this augmenting step does. So again, you look at this path. So this edge belongs to M intersect P, right? I'm looking at my path, and this edge also is also part of matching. So I take them out, but this one belongs to the path P, but it doesn't belong to the matching M. Also, the last edge belongs to the path, but it doesn't belong to the matching. You are at them to the matching, that is the symmetric difference. So this, again, the symmetric difference is nothing but the formal mathematical term to express what we are doing in terms of the augmenting operation. Okay. You don't have to get frustrated by this kind of definition. All right. Any questions so far? Not. All right. So we can formally prove the following. So again, the idea is that if you apply the augmenting step, you get a matching. Okay. You don't run into two edges that intersect one vertex. You don't run into such an issue. We safely get a matching. And what's more important is that the size of it is one larger than the original matching. We are always improving the size of the matching if you have an augmenting path. What's more important is the following. So in fact, if you have a maximum matching, then there's no augmenting path. Okay. If there's an augmenting path, we know that there's a better matching. So the current matching is not optimal, but the converse is also true. So if there's no augmenting path, then it means that the algorithm, the current matching is maximum. And if you remember the proof idea, so M is not maximum matching, and M prime, let's say this is the maximum matching. So because M is not a maximum matching, we know that the size of M and M is smaller than the size of M prime. This is all we know. And the idea was to take the symmetric difference and this maximum matching M prime. And again, if you look at the graph or the subgraph spanned by the edges of the symmetric difference, it has degree, each vertex has degree at most 2. Okay. That was the key point. If you have every vertex have degree at most 2, then it will be a union of cycles and paths. And in fact, each cycle and path has to be alternating. So you have to have a structure like this. And also, you cannot allow an odd cycle because it has to be alternating structure. So every cycle has to be even, but it can have paths of an arbitrary length. Okay. But you must have a path that has more edges in M prime than M. That's because if you look at a cycle, the number of blue edges and the number of red edges are equal, right? But we know that the number of edges in M prime is greater than the number of edges in M. So you have to somehow have more edges in blue. And the only way of having more edges in M prime or blue has to be with this path that has a more blue edges. Okay. So, but each path has to be alternating. So if you have more edges in M prime, it has to be something that end with both blue edges. Okay. But if you turn it into the original graph, it will be on augmenting paths in terms of red edges. Okay, so this is on M augmenting path. So this is basically the proof. So based on this theorem, we have this algorithm. So you start from an empty matching, and then until you don't have an augmenting path, you find an augmenting path and augment the edges of it. And then if you run into the point where there's no augmenting path, by this theorem, we have a conclusion that the current matching is maximum. Okay. That was the augmenting path algorithm. And okay, one note is that the number of the augmenting steps is boundable by number of vertices divided by 2. This is just because each matching has size at most number of vertices divided by 2, right? Because each edge can consume 2 vertices in your graph. So that's this. This is a trivial bound on the size of the matching. And every time you take an augmenting path, you are increasing the size of the matching by 1. So this is basically the upper bound on the number of augmenting steps. Now, the question is, how do we find an augmenting path? Okay. And then one audience was asking a question about where is this property of bipartition is used in this algorithm. Somehow this template doesn't rely on bipartite structure at all. Okay. So in fact, we are using the bipartite structure when you are trying to find an augmenting path. Okay. And in fact, this algorithm outline will be used for non-bipartite graphs, the basic outline. But there we have to kind of think about some issues about odd cycles and when you are trying to find some augmenting path. Well, I'm going to explain that later. All right, so to find an augmenting path, we were using this structure called the alternating tree structure. Okay, and the idea is that we take on exposed vertex. Right? If you don't have an exposed vertex, it means that your matching is perfect. It means then it automatically implies that your current matching is maximum. If your matching is not maximum, then you must have an exposed vertex like R here. Okay. So this is exposed. So it's not connected to any of this matching or red edges. So you enumerate all neighbors. And the neighbors are attached by these black edges like this. So you take R and you enumerate all the neighbors like this in this graph. But if you have an exposed vertex V prime as a neighbor of the exposed vertex R, then it means that you get on an augmenting path. It's a trivial augmenting path. There was a question about, well, the edge doesn't look like it's having an alternating structure because there's no matching edge. But well, that's the trivial alternating path without a matching edge. If you have on 2 vertices that are both exposed, you can always add an edge here, a matching edge here. So this is a trivial. This is the simplest augmenting path, by the way. Okay, so if you have an exposed neighbor of the initial exposed vertex, then you are done. You found an augmenting path, and you're okay. If you don't have such a neighbor, then all the neighbors of the initial exposed vertex are covered by matching edges. Then you also enumerate these matching edges like this. Okay. Now you look at these edges at the bottom, and you treat them like exposed vertex. Okay. Now you look at the neighbors of it, and you enumerate all of them. Now the enumeration, it has to be done with black edges, because each vertex can be part of at most one red edge. So the edges at the bottom has to be black. Now if you also find some V prime that's exposed, then it means that you found on augmenting path like this. Okay, that's good. So if there's no exposed vertex as a neighbor, then it means that they are all the neighbors of this one are matched. Then you can also enumerate the matching edges below like this. Then you increase the graph, this tree structure like this. Okay, and you stop when all these vertices at the bottom, which are called leaves. They do not have neighbors that are not explored. Okay, if all the neighbors are explored and they are found in this tree structure, then you are stopping your search. And is there any question? Okay. So growing this tree structure is not too complicated, but the analysis can be a bit more, I guess, tricky. So let's go over the analysis together one more time. So, okay, and this is called, the first level is level 0, and the next level is called level 1, and level 2, and 3, and 4. And what's interesting is that the size of level 1, level 0 is always 1 because it's the root node, the exposed vertex. And the size of the level 1 and size of level 2 are equal. This is because of the way we enumerate the edges for the odd level. So you have these neighbors of exposed vertex, and when you grow to the next level, we are using the matching edges. So each vertex at level 1 has to be matched with one vertex, because that's the definition of the matching, right? So, and also if you have level 2 or level 3, the size of level 3 equals the size of level 4. We have this property. Okay. Now what I'm gonna do is, we have this tree, and W1 is the set of vertices from all even levels, and V1 the set of vertices from all odd levels. Okay. Great. Note claim 1. We know that W1, the size of W1, which is the number of even level vertices, is 1 larger than the number of odd level vertices. Okay. Again, this is because of this argument at the bottom right. So we have one vertex which is exposed, and then each odd level and the next even level can be paired, and they have the same number of vertices. Okay. This is claim 1. And claim 2 is the following. No two vertices in W1 are adjacent. Okay. Which means that if you take two vertices from W1, they cannot be connected by an edge. Okay, the reason was that, let me give you one example and then I'll explain formally. You have these two matching edges. Let's say I have these two even vertices. If there's an edge between these two, let's say these two vertices are U and V, then you create an odd cycle. In fact, this is the argument. Because U is at an even level, there's a path from R to U of an even length. And also, because V is at an even level, there's an even length path from R to V. Right? And the length of the UV path, which is the edge, is 1. So if you, then this means that you have a closed walk of an odd length. Some vertices can be repeated. Okay, so that's a closed walk. Or you can prove that on every closed walk of an odd length has to include an odd cycle. That's not repeating any vertices. There's an odd cycle. And if your graph doesn't have an odd cycle, it has to be bipartite. Okay. I had dinner with the organizers of this event last night, and one student got this question wrong. So basically, you have this cycle, and this doesn't look like a bipartite graph, but this has to be bipartite. That's because there's no odd cycle in there. Okay, it doesn't look like you have this two set of vertices where the edges are present only between these two sides. It doesn't look like this, but this is a bipartite graph because there's no odd cycle. And the reason why is that if you fold this paper into half using this diagonal edge, then you can create something like this. Okay? This is not that important, but well. But I got this question wrong when I was a student. So anyways. Okay, so any questions so far? Again, there's one more even vertex than odd vertices. And we know that there's no edge between two even level vertices. So this is the point where we use bipartition. Bipartite. So we don't have this claim for non-bipartite graphs, if you want to remember it. Okay, I'll come back to this. But the next claim, which doesn't, and this claim doesn't rely on bipartite structures. Claim 3 is the following. Let me draw an example. If you take two vertices, okay, right. So this is first tree 1. Now you are done with your search. If you have this tree without finding an augmenting path, then it means that there's no augmenting path starting from this exposed vertex R1. And what you do is you take out all vertices from this tree, and start your search with another exposed vertex, and you grow your tree. If you find an augmenting path, then you're okay. If not, you're left with this second tree, and you keep doing this process. And let's say there's no augmenting path, and you are left with, let's say, K trees like this. Okay, and I want to claim that there's no augmenting path at all. I want to claim that this current matching is maximum if you don't have any augmenting path like this. Okay, and to show that the claim is the following, I take two vertices from this even level from whichever tree you take. We know that if you take two vertices from the same tree, there's no edge. So I'm taking one vertex from tree 1, and I'm taking another vertex from tree K. And my claim is that there's no edge between these two. Okay. So no two vertices from W1 union WK are adjacent. And the reason is quite straightforward because of how we grow our tree. Okay, so the reason is that, let's say I have this W1 and I have V1. Let's say I have this vertex. So this is U, and I have V from WK, and I also have this matching edge in WK, in tree K, and this is tree 1. And by our assumption of how we grow our tree, we know that the tree 1 is maximal, and tree K, this vertex V, is not part of the first tree. Okay, but we are assuming that U and V are connected. Then let's look at this U when you grow your tree. The U is connected by some matching edge, and it's enumerating all vertices which will be included in the next odd level. We are assuming that there's this vertex V that's connected by a matching edge, and U and V is connected. If we have this situation, then V would have been included in tree 1. Okay, but somehow V was not included in tree 1. So that means that there's no edge between U and V. So this is the idea. Okay. So if you have all these claims, then we have this graph. So basically, if you have an edge, we have this graph that's enumerated by this tree structure, and there's no edge between two vertices at the bottom. We don't have one edge like this. Okay. So now, then every edge is incident to vertex in V1 union VK. Okay, what it means is that it can be either crossing the partition, or it's fully contained inside the top set of vertices. It cannot be fully contained at the bottom. Okay, so let M, so this M is the matching. Now I want to compare the side of the matching. Okay, remember that each edge in a matching, if you have two different edges in this matching, they cannot overlap. They cannot share a common vertex. What it means is, but each matching edge has to touch one vertex in the top set. Okay, so that's basically saying that the size of this matching has to be at most the number of vertices at the top, because one edge in a matching can use at most one vertex. Has to use at least one vertex from the top. But this is the size of our current matching, right? So we for each vertex in the way due to the way we picked we constructed our trees, the number of vertices at the top is basically the number of matching edges. So this is the maximum matching. Okay, any question? Yeah. Right. That's right. What? Yeah. So this is M prime for any matching, but this is also true for this matching M. Yeah. Yeah. Well, let me just remove that. Okay. I already used 35 minutes. Well, this is very important. I guess if you follow this material, then you are pretty much done with this matching. I guess the rest of the materials will rely a lot on this argument. Okay. Any question? I think this is the most structured way of explaining this proof. I think even when I was a student, I think the argument was not that clear, but I guess this. You will not find anything easier than my argument. I guarantee that. With I guess 50% confidence. That's good. All right. Okay. So when I was a PhD student, I had to pass on like English exam to become a teaching assistant or an instructor, and so I had to enroll in some some teaching lessons, and this kind of like just instructors just come up and explain like how to deliver things. And one of the advice is that when I ask for a question, then I have to wait for at least 15 seconds. Like I ask, let's say, is there a question? Then I wait for, let's say, 3 seconds. And if I just continue, then I guess students get intimidated to ask questions. Okay. It's always good to ask questions if you have any. Okay. One more example. Okay. So there were some like students. So I was a PhD student, and there were some kind of undergrad students. Even they are kind of freshman year. They just kind of graduated directly from high school, and they started their first year at college, and they were taking this CS complexity theory course, which is very hard, and I had trouble understanding and stuff from the lectures. But these students, they just show up without any bag. They didn't bring any pencil or anything. They just sit down and they just listen. But somehow, like, if you listen to what they are asking as questions, then you clearly realize that they are understanding and following everything. So, but I was kind of busy writing down, taking notes from whatever the teacher says. But they just kind of sit down and just, listen to whatever the instructor says, and they seem to understand and follow things. So this kind of interaction is, I guess the point of saying this is that I guess interaction is always useful. Any question? All right, that's okay. Question. Okay, I think I waited for like at least 3 minutes. Okay, let's move on. That's good. Okay, so let's start with the real part. So far we talked about how to find the maximum matching. So that has the maximum number of edges in a graph. Okay, so that's useful when you are dealing with situation where each connection, the connections between vertices have equal importance. Okay, like I get married to somebody and some other person gets married to another person. These have equal weights. But maybe that's not the case. Maybe some connection is more expensive than another one. So can we take that into account? Okay. So that can be captured by edge weights. So individual edges can have heterogeneous weights. And the question is to maximize the sum of weights of the edges that you are picking for your matching. Okay, so if you have equal weights of 1, then the total weight sum will be the number of edges, or you can also have different weights. So then the new objective is to maximize the sum of edge weights given in this expression. So W subscript E is the weight of edge E, and you are summing off over the edges in this matching M. Okay. And this is called the maximum weight bipartite matching problem. Okay. We can, there's a way of extending the previous augmenting path algorithm to this weighted case, but I'll not discuss that. But instead, I'll give you something different from this combinatorial algorithm, and that will be based on something called the optimization problem. Okay. I guess the title of this course is combinatorial optimization. So it has, as I said yesterday, there are 2, I would say, like orthogonal directions. The one is purely combinatorial. You work over this kind of vertices, edges, like we did for analyzing the augmenting path algorithm. But there's a completely different, maybe not completely, but there's a little bit different way, which is based on this kind of formulating the problem as some linear program or integer linear program, which I will explain in a minute. So this is the other approach, which is different from the combinatorial way. Okay, so what is a linear programming, or what is an optimization problem? Okay, I will just let's go through that one by one. So to define an optimization problem, we need to define some decision variables. Okay, so we have on edge E, and we take variable xe, just indicate whether this edge E is part of my matching or not. Okay, so if so this variable will have value 1 if I decide to include this edge E in my matching M, or 0 otherwise. Okay. Then this vector has length E, where E is number of edges, and this is called the incident vector, or the characteristic vector, or even it's called the support vector. So it's an incident vector of this set of edges that you pick. Okay, this is just the terminology. So a subset of elements can be encoded by this 0, 1 vector based on like whether you pick an element or not. Okay, any question? Okay, then this weight sum of the edges in your matching M can be equivalently written with this expression. So WE times XE. Now the summation is over all edges. And whether you pick your edge in your matching M or not, is captured by this variable xb. Okay, you are only taking, weights where the corresponding variable has value 1. Okay, so this is the variable part. Now you need to write down conditions. So not all 0, 1 vector corresponds to a matching. Okay, it can be like, let's say, let me not. Okay, if you have, let's say, 3 edges, but if you pick two edges, then the corresponding 0, 1 vector will be 1, 1, and 0. If you enumerate the edges from top to bottom, this one is a 0, 1 vector, but this does not correspond to a matching. Now then, the question is, how do we guarantee that you find a matching? How do we impose your condition that this 0, 1 vector corresponds to a matching? And what we use is the following. So for each vertex u, it can be incident to at most one edge in the matching. Okay, you can pick at most one edge or at most one neighbor to match with your chosen vertex u. And that can be captured by this inequality. Okay, what it is so you have a vertex u, and you look at all neighbors of it. Let's say this is v1, v2, and vk. Then you have xu v1, and you have xu v2, and you have xu vk. The summation of these variables has to be at most 1. And the reason is that you can pick at most one vertex or one edge that's matched with this chosen vertex. Okay. And this is equivalent to imposing that the degree is at most 1. And that's why this is called a degree constraint. Okay. Great. And in fact, this is enough. This is enough to guarantee that you find the matching. So you have a graph, but that doesn't have to be bipartite. Now you pick a 0, 1 vector. Then this thing corresponds to a matching if and only if it satisfies this degree constraint. You can argue this. I leave it as an exercise. It's not too difficult. Again, the conclusion is that adding this constraint, adding these inequalities is enough to impose that what you find is a matching. Okay. There's no conflict between two edges if you, after you impose this condition. Any question? Okay, great. So this is the optimization problem. So we want to find the maximum weight matching. So we have this objective of maximizing the total weight sum. And I take 0, 1 vectors that satisfy this degree constraints. Okay. So this is the optimization problem. Again, it has 3 components. You have the objective and constraints and variables. And the objective function and the constraints are written in terms of the variables. And the meaning is that, you want to select a vector that satisfies this 0, 1 constraint and the degree constraints that maximize the total weight sum. Okay, and that gives you the that always computes the maximum weight matching in G. And the proof of this statement is that if you have so we argue that any 0, 1 vector satisfying the degree constraint has to correspond to a matching. And among them, you are finding the one maximizing the weight sum. Okay. Let me go back to the previous slide. And this thing is, again, so I said that this thing is called the degree constraint. And the condition that each variable takes a 0, 1 value is called the binary constraint. Binary means like 0 and 1. Okay. You know, let's look into what's written for this optimization problem. I'm just throwing away some terminologies. So the objective function, okay, and constraint, they are written in terms of variables. And not only that, they are written with linear functions in X. Okay. What is a linear function? A linear function has this form. So this is high school student. Are you familiar with this notation? Transpose. Okay, that's good. That's good. Yeah. So if you take like the undergrad linear algebra, of course you get to know this. I mean, you already know that. Yeah. Okay, so C transpose X is just just you are taking the component wise multiplication and just sum those values up. And if your function is written in this way, that we say that the function is linear. Okay. Now you know that this is the summation of the weighted sum of variables, and also the constraints have summation of variables, so they are linear functions. Okay. But okay, so if your optimization problem consists only of linear functions, then with the corresponding optimization problem is called a linear program. But this is not a linear program because we have this binary constraint that takes some discontinuous values for that's assigning a discontinuous value for the variable. So, but this is called a binary linear program. This is almost a linear program except for this binary constraints. Okay. So except for the constraints that are assigning some certain values on variables, except for those things, if you have linear structure, then you say that the problem is a binary linear program. Okay. And in general, you can also model like general integer quantities, not just 0, 1. It can be 1, 2, 3, 4. If you have constraints like that, then the corresponding problem is called an integer linear program. Okay. So students at KAIST, I'm offering a course on integer programming next semester. Okay. If you are interested, you can take it. All right, great. So, and I'm not gonna talk too much about this complexity throughout this course, but integer linear programming in general is an NP-hard problem. And NP-hard, I'm not gonna get into the definition of what this NP-hard means, but it means that it kind of implies that it's a hard problem. Okay. So unless your problem is too important, maybe using an integer program is not the best way to solve your problem. If you're okay with approximating your values or variables with some fractional quantities, then maybe it's good to approximate your problem with something continuous instead of solving this integer program, just because this is a hard problem. Okay. But having or keeping integer quantities is really important. Then you have to use this integer programming formulation. But if you're okay with approximation, then perhaps a continuous method will be better. And that's what people in, I guess, machine learning community does. Okay. But some problems, even though they are discrete problems and they are defined over these 0, 1 variables, sometimes they are very fast algorithms for solving them. But that's not always the case. So for certain structured problems, maybe you can design a better algorithm. That's always a central question in this literature. Okay. And we're going to discuss one more thing, which is submodular minimization. Submodular minimization is a kind of discrete optimization problems, but there's a fast algorithm using a continuous method. Okay, that's what we're going to talk about. Any question? So the question is about do we have to look at vertices? So I'm enumerating all vertices in the vertex set V. So I'm not looking at the directions. I'm looking at, so this is an undirected graph. So you take any vertex and enumerate all neighbors, and you impose the condition on you. This could have edges from this side too, but there's no direction in this graph. You can model your bipartite matching problem with flow problem. Then you can impose directions, and the conditions and inequalities can be written in terms of going out and going in. But this is an undirected case. So there's another formulation based on network flows. Then you need to you're considering directions, but for this formulation you don't need one. Yes.
So there's only XUV. There's no XVU.
No XVU. It's XVU and XUV, they are the same. Yeah. Right. So the question was about whether the integer linear program is something more general than binary linear program. The answer is yes. Yeah. Right. But I guess for those of you who are interested, I guess the most of the important theory is built on the binary case, and it will easily extend to the general integer case. But the central question in the complexity theory is that, well, okay, so binary linear program, there are 2 to the n number of solutions, because you have n variables. For each variable, there are 2 choices. So the total number of solutions is 2 to the n. A naive algorithm is to enumerate all possible solutions, and that will be 2 to the n. But for general integer program, even though you have n variables, the number of choices could be large. Your variables could be unbounded. But the open question is, can you solve one general integer program in 2 to the n time? Well, but that's open for 7 years. Okay, and many people in the community is working on that. But in terms of practical perspective, like software and solution method, like practical algorithm and so forth, they are all relying on the techniques from 0 and binary case. Okay. But complexity perspective is different. Okay. Any other question? Okay. I'm really behind the schedule, but that's okay. Okay. Right. I decided to go slow. Okay. I guess I was working too hard on preparing materials last night, but I was too tired. So it's okay to go slow. But I guess I have enough materials ready for the rest of this course. Anyways, but in contrast to integer programming, linear programming admits a polynomial time algorithm. I'm gonna mention what's called the ellipsoid method later. I'm not gonna get into what the algorithm does, but I'm gonna discuss the consequence of the ellipsoid method for combinatorial optimization. If you have heard of the separation between optimization, they are equivalent problems, but the proof is based on the ellipsoid method. I'm gonna get into that. And also we have this interior point algorithm, okay? So I think, so if you want to join a software firm developing an optimization solver, I guess on interview or would typically ask questions like, can you, so there are 2 different algorithms for solving a linear program. One is the simplex method, and the other one is called a barrier method. And the barrier method is an interior point algorithm. And you're required to implement these 2 different algorithms for linear programming. And a typical solver for linear programming are basically combinations of barrier method and the simplex method. And interior point algorithm is one of them. Is a variant of the barrier method. Okay, so let's move on. So we have this integer linear program formulation for bipartite matching. And we know that linear programming is easy, but integer programming is hard. So the common way to tackle an integer program is to remove the integer constraints first. Okay, and you end up with a linear program, and take that into account first. And when you remove this integer constraints, the corresponding problem is called the linear programming relaxation. And that means that you remove the constraints. And so you are imposing constraint, you are making your solution set tight. But if you remove these constraints, then the solution set becomes a little bit relaxed. That's why we use this terminology, relaxation. So if you remove the integer constraints and I replace that by non-negativity, so I'm okay with my variable to have non-negative values instead of just 0, 1 values. But because you have this degree constraints, any edge has to appear somewhere in the degree constraint. So because of this constraint, each variable has to be at most 1. So you don't have to write down that e at most 1. That will be implied by one of your degree constraints. And so this is called the LP, or linear programming relaxation of the binary linear program. So this is an easy consequence. So if you take the relaxation, what you do is you had a solution space like this. Let me just write down just arbitrary values. And now you're replacing the solution set by something continuous like this. You are taking a larger solution set. Okay. Previously, you were looking at only these discrete values that are expressed in terms of dots. But now you are looking at a larger set of solutions. And because of that, if you solve this relaxation, its value is always an upper bound on the original value for the maximization case. Okay. So that means that if you solve this linear program, it gives you an upper bound on the maximum weight of a match. Okay. But the issue is that if you solve all this linear program, there can be some variables that are strictly between 0 and 1, because you're not only allowing 0 and values, but you allow some fractional values in between 0 and 1. Okay, that's an issue. But the interesting statement is the following. But if you have a bipartite graph, let's say you solve this linear program and get an optimal solution, then you can find maximum weight matching using that solution. And that is the next theorem. So we have a bipartite graph. And we have some arbitrary weights. You can allow negative weights as well. Now you solve LP relaxation, which is a linear program. Okay. Maybe your algorithm, like the barrier method or the interior point method or the ellipse width method, doesn't give you a solution that has 0, 1 quantities, but you can always construct a solution that has only 0, 1 values. So the LP relaxation must have an optimal solution that has integer quantities only. Okay. And not only that, we can find the maximum matching out of it in polynomial time if you solve on LP. Okay. Is there any question?
We need to assume that weights are all non-negative.
You don't have to. You don't have to. You just so what I'm gonna do is you just solve an LP, and on LP can take negative weights. Okay, and what I'm going to do is I'm going to construct another solution that has the same objective value as the first one. But the requirement is that that solution has 0, 1 values. So the question was about the weight. Should the weights be all non-negative? The answer is no. We can take negative values. Yeah.
What's the difference between the second sentence and the third sentence?
Okay. So it means there exists an optimal solution. It's about the existence. Now the question is, how do we find it? And the proof, the proof is written in terms of in the algorithmic sense. So if you read through the proof, it gives you an algorithm. That's what I'm gonna do. Any question? All right. Okay, let's go over the proof. Let's say I have an optimal solution, X bar. So a black box algorithm gives you an optimal solution. But the issue again is that you can't take negative the fractional values. Now what I do is I take the set of edges that have positive values in my optimal solution X bar. Okay. You just ignore edges with 0 values. I only keep positive values. Okay. It could be 0.5, 0.1, or 1, but I just ignore 0 edges. Okay. Then, I want, if this is a matching, then I'm good. But in general, because these values are fractional, and I include all of them, it could be the case that I take all edges of the graph. In particular, it could have cycles or large trees. Okay, and the proof, then what I want to do is to break all cycles and trees, so that at the end I want to be left with the matching edges that are vertex disjoint. Okay. This is the idea. And in fact, the proof is quite straightforward. Let me explain how we do it. So I'm going to explain how to break cycles. And later, I'm going to explain how to break trees. Okay. So let's say I have a cycle like this. Note that this has to be even because so we have a bipartite graph. And I have these edge weights written in this way. Okay. And if this is a cycle, you can argue that all edges have values strictly between 0 and 1. Okay. So if you have an edge has value 1, then the neighboring edges will have value 0 because I have the degree constraint. So if you have a cycle, then all values are fractional. Okay. And what I'm going to do is the following. I'm going to take the minimum value. So let's say I have cycle C, even cycle C with 2k edges. And I'm going to take delta to be the minimum value of the corresponding E. And E belongs to the cycle. Okay. I take a minimum value of this X coordinate over the edges of the cycle. Okay. Then claim is that X bar E has to be, first of all, by definition of delta, it has to be at least delta because we took a minimum value. And it has to be at most 1 minus delta as well for all edges on the cycle. And the reason is that, xe bar plus xei, and its next set, xei plus 1, has to be at most 1, right? Because ei is one edge and ei plus 1, its neighboring edge, and I have this vertex. And then if you look at the degree constraint around this vertex, then these two variables will appear at the same time. They has to be at most 1. And we know that this thing is at least delta, because delta is a minimum value. If you move it onto the right-hand side, then the other variable has to be at most 1 minus delta. Okay. Great. So then what I'm going to do is the following. So I'm going to construct two variables. So one, let's say I have, let me explain it with this rectangles. So what I'm going to do is, for one solution, I'm going to add delta, and subtract delta for, I'm going to do this alternating procedure. Okay. And also, for the other solution, I'm going to add delta here and subtract delta here. And that's basically x tilde, x hat over here. Okay. So delta here is, in this example, is 0.2. I had to use different colors. Sorry. It's not to confuse you. Minus, 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 plus, 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 plus. Okay. So adding delta is not a problem because each value is at most 1 minus delta. And subtracting delta is not a problem either, because each value has value at least delta. So x, if you do this operation, you create two solutions, x tilde and x hat, and they are both feasible. They are both solutions to the alpha relaxation. Each variable has value, okay, x hat tilde e, and x hat e belongs to 0, 1 for all edges in E. And also for the degree constraint, I don't have any problem because I care about vertices on the cycle. And because I alternatively added delta and subtracted delta, the summation of the variables around each vertex will remain the same. Okay? But, okay, let me claim x hat. If you add x tilde and x hat, that's 2 times x bar. Okay, this is what I know. And in fact, let's look at the objective. Then W transpose x hat, which is a summation of the variables, weighted summation of the variables. I know that this is an optimal solution, so this has to be at least W tilde x, W transpose x tilde. This is because x hat is an optimal solution, and also W transpose x hat is at least W transpose x hat. X bar is optimal, right? But if you add these two up, you have 2 times W transpose x bar, at least W transpose x tilde plus W transpose x hat. I just added this in two inequalities. But then from this claim, If you multiply W on both sides, it implies that this is equals 2 times W transpose X bar. You have, and now you have these equalities. So the equalities hold throughout. So W, so this implies that W transpose X bar equals W transpose X hat equals W transpose X hat. So X tilde and X hat are both optimal solutions. But if you look at X tilde, I broke one cycle. Okay. Now you keep repeating this procedure, you can break every cycle in your graph. Let me stop here and I will resume in 15 minutes.